Today's lesson focuses on interpreting and sketching graphs. And our learning goals are, well, to interpret graphs accurately, to sketch graphs accurately of different scenarios, and to describe the properties of graphs. To start this lesson, we're going to look at interpreting graphs and what could be represented by different sections of graphs. So if you'd like to pause the video and draw this, feel free to do so, and you can also try these questions. We're also going to look at the properties of graphs. And so every graph should have a title, and I haven't put one on there yet. So for this first example, I'm going to simply just say, taking a bath. And without a title and without the axes labeled, then we don't really know what we're looking at. So when I'm thinking about taking a bath, what two variables could be compared? Well, in this case, we're going to be looking at what's the height of water, and we will look at that in inches. So we always want to label our axes, and that is on our vertical or our y-axis because that is dependent on the time. And in this case, we'll look at it in minutes. And so you notice I put the units in parentheses because, again, that really helps whoever's looking at this graph to understand what they're looking at. And I've labeled these different sections, O, A, B, C, D, E, F, and G. All right? So when it comes to describing what could be happening in each section, well, from O to A, what's probably happening is we see a steady increase in the water height. Well, that would probably mean that we are just filling the tub of water. A to B, reasonable estimate could be, well, maybe getting undressed, whatever. B to C, what's happening in B to C? Many people would just say that you are getting into the tub. From C to D, long period of time, about 20 minutes. Well, we would assume that you're actually bathing. Notice that B to C is getting in because it's a very, very instantaneous increase. Water level does not change here, so that person did not get out during that time. And from E to F, if I'm trying to describe what could be happening in that, clearly they've gotten out of the tub because the water level returned to its original height before getting in. E to F could be just drying off. Now, when we're interpreting graphs, it is important to recognize that there are multiple answers sometimes. And so in this case, I gave this question my first year teaching on a math test, and a student decided to offer this response to this graph. So O to A, Dad gets in the tub and turns on the water. Well, yeah, that makes sense. A to B, Dad relaxes. Okay? B to C, Mom gets in the tub. And I was like, well, I guess that's true. That can work. Don't need to read any other things that are happening. 2 out of 2. So as long as you can justify each section of the graph, then I think that that's reasonable. Good critical thinking. How long does it take for the bathtub to drain of water? Well, again, if we had a more accurately drawn graph, I would estimate going down that is about 33 minutes, and it looks like it just goes past 35. That was kind of an accident on my part. So I would say 2 to 3 minutes for the water to drain. So again, one of the skills we're looking at, being able to read and interpret different sections of a graph. For this next example, if you're following along and taking notes, you can pause the video and draw out this graph. Notice that we've got this kind of step ladder almost of a grid where it's going hour to hour, and sometimes we have open dots, sometimes we have closed dots. You can also write out these questions and give them a try if you would like to do so. So, as we said on the last example, we always want to have a title. And a pretty standard way to write titles when you have your two variables is to do the dependent variable versus the independent variable. So in this case, if I were creating a title, I might say daily parking fee versus time. I remember doing science labs in school, and that would always be my standard way of writing out a title for my graph. Okay? And now we got a few questions that we're going to use to, again, interpret graphs accurately. So it says, how much does parking cost for 1 hour, 40 minutes? Well, whenever we have something like that, we're going to go along, when we're given an x variable, I can go along, jump up, and I notice that in this case, for that section, it is $12. Next, it says, why might the graph be drawn like this? Or how would I interpret this? Well, my interpretation as I look at this graph is, what it says is there is a flat rate of $6 per hour for parking. So it doesn't matter whether I do it for 1 minute or 59 minutes, I'm spending $6 on parking. But once I hit that 1 hour mark, it's jumping to $12. At the start of each hour, I'm paying an extra $6. So there's a $6 per hour flat rate for parking. Okay? And why might this pattern change after 6 hours? Again, we don't know for sure. We see in our title and in our axes it says daily parking fee. And I see this arrow meaning that it's not going to continue to jump. What I would assume is that there is an upper limit. So there is a max rate or max fee of $36 per day, which is pretty standard in many parkades in bigger cities and things like that. For this next example, we have just the title hot dog sale. So again, looking at our last example, we could also have put profit versus number sold, but because I didn't say number of hot dogs sold, hot dog sale kind of gives a bit more context for what this problem is. And we have 5 ordered pairs on the graph, one at 0, -50, one at 8, 0, one at 16, 50, 24, 100, and 32, 150. Okay? And so, as always, you can pause the video, try these problems before we go through them together if you'd like. So it says, what is the profit if 16 are sold? Well, these first couple questions, pretty straightforward. We simply go over, if I'm given an x value, and go up, and I notice that that is $50 profit. It says if $100 is made, how many are sold? Well, we would go to up to our 100 from 0, go over, and then come down, and we would see that 24 were sold. Now, next question, how much is one hot dog? This is tapping into a concept called slope, which we will look at a lot more later on in this unit or in this course. But if you want, well, I know that I get $50 for every 8 hot dogs that I sell. So if I go $50 divided by 8, that means that I am selling each hot dog for $6.25. Next, why do negative y values exist? Well, again, this is more of an interpreting question. Why would the profit start in the negatives? Again, most of the examples we've looked at so far have been in quadrant 1, where both our x values and our y values are positive, because most real-world examples deal in positive numbers. But that doesn't mean we can't go into quadrant 4 or quadrant 2 sometimes if we have negative values. Well, why are there negative y values here? Because there are startup costs. If I'm running a hot dog sale, I need to buy the hot dogs, the ketchup, the buns, whatever, and so therefore in this case, it costs $50 to get us started, so there is a $50 startup cost. For our last question, it says, why is the graph discrete? Well, I would say that this graph isn't even perfectly or accurately drawn, because I've only given you 5 ordered pairs. And in reality, what I should be doing is put 7 dots between each one of these, because we know that in a hot dog sale you can buy a single hot dog, and so it's discrete because I can't sell a quarter of a hot dog or a 16th of a hot dog. And if I were to connect this with a line, that would suggest that I could sell any fraction of the hot dog and therefore get a different amount of revenue, which just isn't realistic for this point. So I'm going to say something to the effect of can only sell whole hot dogs. And again, some of you might say, well, what about half hot dogs? We could maybe every second, well, go ahead and draw twice as many dots if you want, but we would not have any fractions beneath that. For this last example, we're going to talk about bungee jumping. And I said given the graph of height versus time, create a corresponding graph of speed versus time, but we're going to draw both graphs together and be able to compare them both. Now I hope that no physics teachers are watching, because this probably won't be accurate to how quickly someone accelerates towards the ground and all that sort of stuff, but I'm just trying to show how we could use one graph to create a similar graph. So meters, let's just say we're going up along my vertical axis. Obviously height depends on time, so I'm going to go up by 10-meter increments that way. And I'm going to go up on the time scale. I'm going to say 2 seconds for every tick. All right, so there we go. I've gone up to 16 seconds. And let's just think about, well, bungee jumper, let's say, starts at 45 meters up and jumps. And obviously they're going to accelerate down. Now, would I want to hit the x-axis? Maybe. If, let's say I'm diving into water like you can do in New Zealand. But if it's just ground, definitely don't want to hit the ground. So I'm going to turn around at 4 seconds, come up. I'm going to come probably about halfway up. Definitely not going to come all the way back up to that platform. Let's say that goes up till about 7 seconds. And then I'm going to turn around and drop back down. Let's say that the next turnaround point is at 10 seconds. Back up 12 seconds. Back down 14 seconds. And now just kind of another little loop. Something to that effect. Okay? Now, we're going to use this graph to create a similar graph. But the reason why we're doing this is because it's so important to understand what you're actually comparing. So now I'm creating a speed versus time graph. Well, time better stay the same. If I went up by 2 seconds here, I'm going to stay consistent and go up by 2 seconds here. Hope that makes sense when I'm creating a corresponding graph. For my speed, well, I might want to do a little bit of math and say, okay, if I went, let's say 45 meters in 4 seconds, that's about 11 meters per second. But I'm probably going to get a bit faster than that at certain points because I don't start going that fast. So let's just ballpark it and say that I get up to 18 meters per second. I'm not sure if that's really true, but maybe I just hit that max point before the cord actually starts to pull on me. Again, physics teachers, be gracious. And now, I want to identify certain points that are key in this example. Well, my speed at the start, well, I'm standing on a platform, that's going to be 0. I have a speed of 0 at any other moment in this experience. Hopefully you see that the answer is yes, because as I'm dropping down, and that cord is extending, right before I start to slingshot up, I'm motionless for a second. Then I come up. So my speed would again be 0 at 4 seconds. Now what happens between 0 and 4 seconds? Well, I speed up really quickly, and then as the cord starts to pull on me, I slow down. So I said, let's say 18 meters per second, so I'm going to shoot up to 18 meters per second and then back down to 0. So that's my first loop. Now, am I motionless at any other moment? Well, yes, I am. I get shot back up, cord's pulling me up, and just before I start to fall again, I'm motionless. So at 7 seconds, I'm motionless. What happens in between those two? Well, obviously, I speed up, probably not to the same velocity, but something to that effect. At 10 seconds, I'm motionless. And again, every time, 12 seconds, 14 seconds, I'm motionless because those are the turnaround points for the cord. Okay? And each time my speed would not be, or my velocity would not be as pronounced, but it could be something to that effect. Alright, so this is an example of how we sketch graphs or sketch relations. and hopefully that comparison makes some sense to you. Again, always look at the axes, that's key. So I hope that this lesson has taught you how to consider properties of graphs, how to draw graphs, how to interpret graphs, and we'll see you next time.